Here we go. So lesson 54 is on the product and quotient of complex numbers. So we kind of did something similar to this in Algebra 2, but we're going to expand on what we know from Algebra 2. So let's start with the basics. So in Algebra 2, when you guys have things like 3 plus 2i multiplied by 2 minus 7i, right, we just distribute, like we FOIL this out. So we would have 6 minus 21i. Oops, I forgot my 1 there. 21i plus 4i minus 14i squared. So remember that. And then we would combine our like terms. Now when we combine our like terms, we remember that I squared, if it's -1, perfect. So we're going to have 6, and then we're going to have minus, so we have 21 plus 4, so that's going to be minus 17i. And then this minus 14i squared becomes -14 times -1, which is plus 14. So we end up with 20 minus 17i. Easy? You remember that? Good. All right, and division was a little bit harder. So if you had 1 over 3 minus 2i, we multiplied by what we called its conjugate, right? So its conjugate was 3 plus 2i. So basically the sign in front of the I changes, but the other sign does not change. It's not like -3 plus 2i. Okay, so remember this is called the conjugate. The complex conjugate. So when we FOIL that out, we end up getting 3 plus 2i, and then on the bottom we're going to have 9. Our outer and inner become positive 6i and negative 6i, so they cancel. And then our last becomes minus 4i squared. And we like that those cancel, right, because that's why we multiplied by a conjugate. We wanted to get rid of the I terms on the bottom. So at first glance, it still looks like you have an I term because you have I squared. But remember, I squared is -1. So we have 3 plus 2i over 9 plus 4, which becomes 13. And in Algebra 2, remember, I had you guys write this in A plus BI form, and I didn't really explain why we did A plus BI form, but remember how we just graphed complex numbers last time, and we had that real part and imaginary part? If I was going to graph this, I wouldn't go over 3 and then up 2, right? How much would I go over to the right and up? Yeah, that 3 over 13, right? So we got to write this as 3 over 13 plus 2 over 13i, because then if I wanted to find r and theta, I could find r and theta and write it in that r times cosine plus I sine form. The cis. Do you remember the cis stuff? Did you guys write cis on your homework? It saves some time, doesn't it? All right, so if I have 4 minus 3i, I can't just bring that squared in. I have to actually FOIL it out. And hopefully, after having me for 2 years of math, you guys know not to just bring in that squared, right? Good. If I've taught you anything, I hope it's that. All right, so we have 16. I'm going to FOIL it out, so I have minus 12i, and my inner is also minus 12i, and my last becomes plus 9i squared. So I get 16, I have minus 24i, and this 9 times -1 becomes minus 9, which becomes 7 minus 24i. Okay, so I made you go through that torture in Algebra 2, and then I think after I did that, I taught you guys that you can do it on your calculator as well. Do you guys remember that? So pull out your calculator and I'll show you how you can do that. So the key is that we go to Mode, and we want our calculator to be in what we call A plus BI form. So go to Mode, and instead of real form, make it A plus BI. And then get out of there, so we do second quit. All right, and so if I want to do something like 4 minus 3i squared, I would do parenthesis 4 minus 3, and then the I is down where the decimal point is, so you're going to do second and then decimal point to get I, and you square it, and when you hit enter, it gives you 7 minus 24i. So if you wanted to do something like number 2, just make sure when you divide it out, you put parentheses along the denominator, so you have 3 minus 2i inside parentheses, and then you hit enter, and it gives you this. Now this is a little bit strange, right? My calculator is telling me 0.230799, blah, blah, blah. And if I arrow over, I can see like more decimal points, but I don't want it as a decimal. I wanted it to look nice and neat like this. So what do you think I do? Yeah, I hit the fraction button, so I do math 1. And it gives me 3 over 13 plus 2 over 13i. So it's really handy. So I told you about my friend in grad school when I was there who used to do things like to his college students, he'd be like, okay, we're going to do 5 plus 3i multiplied by 4 minus 7i all over 2 minus 6i. Well, that's kind of weird. 3 plus 5i, like things like that. Oh, yeah. And he would make them FOIL that out, and then the bottom would still have an I. So then they have to multiply by the conjugate, right? And it was crazy. That took a really long time. So it's kind of nice to know that your calculator does that for you, so those harder ones. But if you did not have a calculator, how do we do things like 1 minus 3i to the 18th? Okay, so there is a way. And the way that we do this is using these this trigonometric form of numbers, or this polar form of numbers, right? Which you guys did last night. So we're going to go ahead and do that. So we're going to change, actually, let's start with this. Maybe not. I don't know if I have an example of this. We'll go ahead and do this example, it's fine. So let's change this. We're going to call this z. So sometimes we name complex numbers with a z. Did you guys notice that yesterday? I kept calling it z equals. And then we're going to find z to the 18th. Okay, we don't want to multiply that out 18 times. That's crazy. Okay, so what we're going to do is we're going to write this in trig form. I didn't leave you guys much room, did I? So I have room on mine. So we would write it in trig form first, and then we're going to have this trick for, so maybe I won't make you do it on this one since I clearly didn't have too much room. So let's look at this product and quotient of two complex numbers. So if you have two complex numbers, z1 and z2, and you want to multiply them together, it's really, really easy. Okay, all we do is we take our r values, our radius values, the modulus, remember? And we multiply those, r1 and r2. And then in parentheses, I still have like a cosine plus I sine, but the angle that I have is not those thetas multiplied together. It's actually the thetas added together. Okay, so it seems a little weird, but we're going to have theta 1 added to theta 2. And then we're going to have plus I times sine of theta 1 added to theta 2. Okay, so we multiply our modulus. We multiply those radii, and then we're going to add our angles. So what do you think division is going to be? Yeah, we're going to do r1 over r2, and then we're going to subtract those two angles. Perfect. Are you ready for this proof? You just get scared every time I say proof. You know that proofs bring me joy, so we're going to do this. It's not going to be that bad. All right, so if I have z1 is, all of this, and I have z2 is all of this. If I multiply z1 times z2, I think you can see that we would take our r1 times cosine of theta 1 plus I sine of theta 2. Or not theta 2, theta 1. And we're going to multiply that by r2 cosine of theta 2 plus I sine of theta 2. Okay, so we're multiplying those together. Do you guys see that the r's just multiply? Like it's going to be r1 times r2. What do you think we're going to do with the cosine plus I sine parts? We're going to like multiply it out. Not quite squaring it, but we're going to FOIL it, yeah.
Don't you add the two?
I haven't done that yet, yeah.
No, but you said multiply the,
Yeah, so I'm trying to find z1 times z2, so that's a times there still.
but up there we wrote plus I sine theta 1 plus theta 2.
It should be plus, I think. I don't know what you're talking about. All right, I think I'm good so far. I think all of it looks good. All right, so we're going to multiply, and we're going to do r1 times r2. And then we're going to FOIL this multiplied by this. So we're going to FOIL. All right, you ready for this? You're all right. You'll survive. All right, so we're going to have cosine of theta 1, cosine of theta 2. Right, that's our first. Outer is plus I times sine of theta 1 times another I, so I squared, sine of theta 2. Oops, did I mess? I'm not doing my outer, am I? Okay, hang on. So I have I times, I skipped to my end. So I'm going to do cosine times I sine of theta 2. So I'm going to have I times cosine of theta 1 sine of theta 2. All right, now I'm going to do my inner, so that's these two terms. So I'm going to have plus I sine of theta 1 cosine of theta 2. And one last step. It's the last one. I squared, what was I squared? Negative 1, right? So I'm going to have negative 1 times sine of theta 1 sine of theta 2. And as you're starting to think about final exams, you got to dust those cobwebs out. You got to think back to the, not chapter 7, that was vectors, but the chapter before that when we did the lovely identities. And if we had something that looked like cosine, cosine, minus, remember this is going to be minus 1, sine, sine. Do you guys remember what that was? No. So if I had cosine of x, cosine of y, minus sine of x, sine of y, that ended up being cosine of x plus y or x minus y?
That's x plus y.
X plus y, right? So that's what we're using. So we're going to say this R1, R2, that part that I underlined in red becomes cosine of x plus y. In other words, cosine of theta 1 plus theta 2. What about the part underlined in blue here? Well, that's going to be, you really want it to be 1, don't you? Cosine x sine y plus sine x cosine y. Do you guys remember what that was? That was sine of not x minus y, x plus y, right? So it's going to be plus I times sine of theta 1 plus theta 2. Look, we just proved it. Woo, confetti. So what did we just prove? We proved that this product rule works. So when I multiply a complex number, z1 multiplied by z2, I just multiply my r values, and then I don't multiply my thetas, I end up adding them, because it comes from foiling all of that out, right? Does that make sense? Should I do the z1 divided by z2 too? It would bring me such joy, but we'll skip it. So, but you guys understand how that works now. Yeah. Where do I need to go down there? So let's try the first example. So it says find z1 times z2 on the next problem. All right, so if I'm going to find z1 times z2, I'm going to take my two r values, and I'm going to multiply those together. And I'm going to take my two theta values, and I'm going to add them together. We good, Cade? You can peek at KJ's too if you need to. So I'm going to have 20, right, because I take my 5 times my 4. And then I'm going to have cosine of my pi over 4 plus 2 pi over 3 plus I times sine of my pi over 4 plus 2 pi over 3. Okay, do you guys see it? And then I'm going to add those together. So if I have pi over 4 plus 2 pi over 3, I get common denominators, so I get them to be 12. So I'm going to have 3 pi over 12, and I'm going to have multiplied by 4 over 4, 8 pi over 12. So I have 11 pi over 12. So now I'm going to have 20 cosine 11 pi over 12 plus I sine of 11 pi over 12. So you could write that in the shortcut by doing 20 cis 11 pi over 12, right? That's it. We did it. We multiplied those two things together. So the quotient here for number 2, we're going to take our 12 over 6, right, which is going to be 2, and we're going to do cosine of 4 pi over 3 minus 3 pi over 4 plus I sine of the 4 pi over 3 minus 3 pi over 4. All right, we can find those. So if I have 4 pi over 3 plus 3 pi, or not plus, minus 3 pi over 4, again, I can get denominators of 12. So I'm going to have, what, 16 pi over 12 minus, oops, I already was writing a 12 there, wasn't I? Minus 9 pi over 12. So I get 7 pi over 12. So it's going to be 2 cosine 7 pi over 12 plus I sine 7 pi over 12. Or like I said, you could write 2 cis 7 pi over 12.
Wait, what did it be? Minus I sine? This is the quotient.
Nope, it's actually plus. Yeah. Is that what she was saying that I messed up earlier? No, okay, I'm good. Okay, does that make sense? Now let's say you wanted to go a step further. So sometimes these are angles that you can actually get on the unit circle. So like 7 pi over 12, I recognize that that's not a unit circle one, but what if it had been like pi over 4? Then you could go further and you could continue to simplify that down. Does that make sense? Usually I have you guys leave these ones in trigonometric form. So if I say trigonometric or polar form, it's this thing. Okay, so trigonometric or polar form means that. Okay. So polar form makes it very convenient to write powers and roots of complex numbers. Okay, so we're going to talk about powers today, and we'll kind of talk about roots next time. So if I have z is equal to r times cosine theta plus I sine theta, think about how to find z squared. Well, isn't z squared just z multiplied by z? So what would happen then? I would have my r multiplied by another r, so it'd be r squared. What about my cosine of theta? It's going to be like theta plus theta, right? And then I'm going to have I sine of theta plus theta, right? That's what our rule said. It said that we we multiply the r's together, so we end up getting r squared when we do that. And we add our thetas together. So if I have z squared, do you see that it's equal to r squared, and then cosine of not theta squared, but what? 2 theta. Plus I sine of 2 theta. All right, z cubed. What do we think z cubed would be then? R cubed, cosine of 3 theta, right? Plus I sine of 3 theta. Perfect. Do you guys understand where that comes from? It's just from the multiplication rule. Okay, so there's a mathematician that came up with this. I cannot say his name. As Gabby knows, I took 5 years of French and continue to butcher French every day of my life. There's a lot of French mathematicians. So Gabby, how do you think you would say his name? I'm putting you on the spot. Yes, that is exactly right. Did you guys hear her? She said, de Mavre. She had like a rula. I cannot say that, and I always say it the Hoosier way, which is de Moivre's theorem. So I'm sorry if I butcher his name. It's in my head as de Moivre's theorem. And I will continue to say that. But it's really de Mavre. All right, so anyway. So he says, for any complex number, z, so if we have r times cosine theta plus I sine theta, if I want to find z to be n, so any power, what do? We take our r and we raise it to that power. But we take our cosine values and we multiply by n. So it's going to be like cosine n theta plus I sine of n theta. Does that make sense? Pretty easy theorem if you ask me once you kind of multiply those out. I could have proven that. Jeez. Not really. It's easy once it's already around. All right, so we're going to simplify these using de Moivre's theorem, or de Moivre's theorem. So write your final answer in A plus BI form or standard form. So this is a little bit tricky because the ones that I gave you were already in that trigonometric form. Do you guys see how this isn't in the trigonometric form? So we got to convert it to trigonometric form. We're going to raise it to the 8, right? And then we're going to convert it back. Okay? It's not really that terrible, but we'll try it. So if I have 1 plus the square, 1 plus I root 3, first of all, let's think about where that is located, and maybe we can save ourselves some time. It's going over 1 and up the square root of 3. Square root of 3 is around like 0.7. Do you guys know if that's a value that we know? Yeah, so we could do tangent. So we could do tangent of theta equals the y value over the x value. I see some people thinking, divide by 2, divide by 2. So the sine is root 3 over 2, the cosine is 1/2 on our unit circle. What value is that? Yeah, it's 60 degrees. And we're in the first quadrant, so we're good. It's going to be 60 degrees. Do we know what r is equal to? 2. Yeah, 1 squared plus square root of 3 squared. So it ends up being 2. So our z is 2 cosine of 60 degrees plus I sine of 60 degrees. And I'm cool if you do degrees, it's fine. It actually kind of helps with degrees on the next section that we do when we start taking the roots of complex numbers. It gets really weird. All right, so if I want to find z to the 8th, I take my 2 to the 8th, and then I have cosine of 8 times 60, which is 480, plus I sine of 480. All right, Ben already found 2 to the 8th for us. What is it? Oh, I thought you were clicking away. 256. So 256. And cosine of 480, that's not really a unit circle value because we usually think of it between 0 and 360. Do you guys remember coterminal angles and all of that? So if you have 480 and you keep subtracting out 360, I mean, we just have to do it once, right? We get 120. Let's write it as 120. Does that make sense? It's like we've gone around once, and then we're going to go around to 120. Whoops, right there. So I'm going to have cosine of 120 plus I sine of 120. And that would be the answer in trigonometric form. So if I said to leave it in trigonometric form, you're good. That's it. Okay? So all of this would be trig form. But if I want you to go further and write it in a plus bi form, we got to figure out what cosine of 120 is. So cosine of 120 is going to be x value on your unit circle that's just slightly off of 90 degrees, right? 30 degrees away from 90 degrees. So what value is that? Negative 1/2 or 0.5, yeah, plus I sine of 120, root 3 over 2. So our answer then should be negative 128 plus root 3, wait, hang on, I got my 128, don't I? 128 root 3 times I. And just don't sneak that I under there. Some people will write 128 I root 3. Yeah.
Sorry, probably dumb question, but how did you get like 480 for the angle?
I took my 60 and I multiplied by 8 to get that. Does that make sense? Do you guys get it? You can check on your calculator, but what's kind of weird about, I can't use my calculator for this because I have this 128 root 3, right? But if I checked and I had it in this polar form, or this a plus bi form, oh man, I gotta go back in there. And I did 1 plus root 3i. So 1 plus, now my mode's not gonna be in the, I gotta change it. My calculator freezes up sometimes, so it takes a sec. So if I have my square root of 3, and then I have my I, and you're like, ooh, I at least want to check that this is right, and I raise it to the 8, I get all of that. At least I can see that negative 128 number. Do you guys see it? But if I try to do math 1 and change it to a fraction, it's not going to help because this isn't a fraction. It's a irrational number, right, because of the square root of 3. So if you're like, is it really 128 root 3? Well, you can do 128 root 3 on your calculator. And you can say, oh, yeah, that's that 221.70, so I'm good. So you can check your answer if you want to, but don't use your calculator to actually do the work, right? We're going to know how to do this because especially with the roots, we got to know how this is related to the roots when we do the next section. All right, so another easiest one to think about where this is located. So think about 1 comma negative 1. If I go over 1 and I go down 1, I'm right in the middle of that quadrant, right? So my angle is going to be either negative 45 degrees or I can call it 315 degrees. Do you guys see that? I think it's 1 plus a negative 1 times I, right? So it's 1 comma negative 1. All right, so you could do your tangent thing on that one. Your calculator would give you negative 45 if you did it on your calculator. So I'm going to make it 315. All right, so my z value is, well, what's r, I guess? Yeah, my r is root 2 because it's the square root of 1 squared plus negative 1 squared. So this one I have root 2. And I'm going to have cosine of 315 plus I sine of 315. Okay, so that's just our normal. We changed 1 minus I, right, to the first. We changed that into a complex number, like this trigonometric form of a complex number, I guess I should say. So if I want to find z to the 6th, I'm going to take that square root of 2 and I'm going to raise it to the 6th. Any guesses on what we have? Without using a calculator, I see you guys all putting it in the calculator. Close. That would be not quite all of them. So think about this, guys. This is what I think about in my head when I'm doing these. Every pair becomes 2, right? Square root of 4. So it's going to be 2 times 2 times 2, which is 8. Exactly. So it's going to be 8. Another way you guys can think of it is, I've been helping a lot of Algebra 2 students lately, and they're doing, they've done a lot of the rational powers. Do you guys remember, like, when you raise it? It's like a square root of 2 is really 2 to the 1/2. What if you have 2 to the 1/2 to the 6th? Right? What happens to these powers? Yeah, we multiply 1/2 times 6, right? 6 divided by 2 is 3, right? Does that make sense? So you could do it that way as well. Sometimes you have extras. Like if I had raised it to the 5th, what would I have? I'd have 4 root 2. Do you guys see that in your head? Because you're like, okay, I'd have 2 pairs. That creates 2 times 2, and then I'd have 1 left over, so it'd be 4 root 2. Right? That's kind of how we do that. All right, so anyway, so this becomes 8, as we said. And then we have cosine of 315 times 6. Ooh, help me out here. 1,890 plus I sine of 1,890. Now, 1,890, I have no idea where that is on the unit circle. But I know that it's gone around a couple times, right? So you can keep subtracting 360 if you want to. But sometimes I find it's better to just keep subtracting 720 if I see it's really big, right? So I'm like, oh, I'm going to subtract 720 again. That's 2 rotations. So I'm at 450, so then subtract another 360. Does that make sense? So we get 90. So I have 8 times cosine of 90 plus I sine of 90. So I'm going to write us a note here. So find coterminal angle. Do you guys remember that term? It means find an angle that ends in the same spot. All right, and then cosine of 90, I sine of 90. Well, we got our unit circle. We're up here. Cosine is 0. Sine is 1. So we have 8 times 0 is 0 plus 8i. So our answer is just 8i. Does this make sense? One more? Or is that it? Yep, one more. So what if they're not nice numbers? Because sometimes things are not nice numbers. We've talked about this. So 4 minus 3i is not one that is on our unit circle. Okay, so we got to go through these steps. We got to say, well, we got tangent of theta is equal to negative 3 over 4. So theta is going to be inverse tangent of negative 3 over 4. And you can do it in degrees. So I'm going to make sure my calculator's in degrees when I do this. So I'm going to do inverse tangent of negative 3 over 4. And I get negative 36.870. Okay, and let's think about that. Is that the right quadrant? Yeah, it was positive and negative, right? So we're in the right quadrant. If you want it to be between 270 and 360, though, like in that our normal 0 to 360, what would we do? Add 360. So we end up getting 323.130. Okay, and sometimes I store that because I'm like, oh, maybe I need this. So I'm going to store it as A, just in case I need it again. All right, and then our r ends up being the square root of 4 squared plus negative 3 squared, which ends up being 5, so that's at least nice for us. So our z is going to be 5, and you can write cis if you want to. I'm fine with that. If you want to write cis and then say 323.130, as long as you understand what's happening, it's the cosine plus I sine thing, you could do that. So if I do z to the 16th, I get the lovely 5 to the 16th, which is going to be huge. I wonder if my calculator can handle it. We'll see. Ah, that's really big. We're going to leave it as 5 to the 16th. And then I'm going to take my 323, that a value that I had, and I'm going to multiply by 16. I'm going to say, wow, that's really big. So 5170.082. Then I keep subtracting things out. So I can subtract 720, or I could subtract 1440, right? Double 720. Keep subtracting 1440. That's 4 rotations around. Keep subtracting 1440. Oops. Almost there. Subtract 720. Are we between 0 and 360 now? Yeah, so 130.082. Everybody with me so far? All right, so that would be my trigonometric form. All right, and we can leave it like that, that's fine. So if I wanted the a plus bi form, I'd have to find cosine of 130 point blah, 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 right, times 5 to the 16th. But that 5 to the 16th is a little large. I shouldn't have made it so big, because we're going to have things in scientific notation. Okay, does that make sense? All right, so sometimes they're not very nice. All right, so I'll give you guys a little bit of time to work on your homework, and then we're going to play a little game. And we might kind of preview that next section too.